In the previous lessons, we have analyzed the different possible solutions to the differential equation for the water profile. We will now see how to solve numerically this equation to calculate the water depth at different locations, by considering first the case of a prismatic channel and then the extension to non-prismatic channels and natural reverse. For prismatic channels, looking at the equation, we see that there are two possible discretizations, either by fixing increments of water depth delta H and looking for the distance delta S to obtain this increment of the water depth, or the opposite, by fixing increments of abscissa delta S and looking for the corresponding increment of water depth delta H. We start with the first option, fixed delta H increments. Let us assume that we know the water profile until point A here, and we look for point B with a water depth H plus delta H. We look then for the distance delta S corresponding to this depth increment delta H. If we select an increment delta H, we can easily calculate the corresponding increment delta S just by calculating the value of the denominator and the numerator for the depth H at point A, so the starting point. And the exact solution that we are looking for is point B here. Doing this, we find point B1. We see that this point can be quite far from the exact solution at point B. So the accuracy of the estimation depends, of course, on the size of the step delta H, but also on the curvature of the water profile, as we approximate it locally by the grain straight line that is the slope of the water profile at point A. To increase the accuracy of the calculation, we could calculate the values of D and N at an intermediate depth H plus delta H half, so at this point M here. This consists in taking the slope of the red straight line, which is actually the slope of the water profile at mid-distance between points A and B. Using this new slope, starting from point A, we find point B2, that is much closer to the real solution represented by the blue point B. So, we see that in order to determine the water profile using delta H increments, we should use values at mid-distance of the delta H interval, as done here. And of course, the size of the delta H increments also play a role in the accuracy of the solution. Let us illustrate the procedure by means of an example. We have a channel with a rectangular cross-section, as illustrated here, and an underflow gate here at the upstream end of this channel. The gate opening is 1 meter. So the question is, what is the water profile that will take place in this channel? We have here the flow condition, discharge, Manning coefficient, and the bed slope. The first step is to calculate the normal and critical depth for this situation. We find these values, and as HU is larger than HC, it means that we have a mild slope. So the water profile will be one of the M profiles recalled here. As the upstream gate has an opening of 1 meter, which is below HC, we see that we will have a M3 profile controlled by the upstream conditions, and these upstream conditions are given by the opening of the gate. So we can now calculate the detailed profile starting from H equal to 1 meter at the gate until the critical depth at the downstream end of the M3 profile, because we know that M3 profiles finish at the critical depth. So, as we know that the M3 profile can only exist up to HC, we know the total depth range over which we should perform the calculations. It is between H equal 1 meter and the critical depth. we decide to calculate it with 10 intermediate points. So the difference between HC and the depth at the gate is divided into 10 delta H intervals, and we have delta H equal to this value. So we can now start filling in the table by calculating the values of N and D for each value here in this column of H plus delta H half. We find the values indicated in the table, and we find that the profile reaches the critical depth after a distance of 932 meters. So in the present example, the water profile does not reach the end of the channel, because the end was after 1200 meters. So this already indicates that the M3 profile alone will not be sufficient to describe the complete flow in this channel. In some situation, we want to know precisely the water depth at a given distance from the starting point. For example, if we need to know the water depth 500 meters from the gate, from the previous results, we could interpolate between the two closest points, so probably these 2 points, but this might not be sufficiently accurate. In such a case, it is more convenient to work with fixed delta S increments, as given in this equation here. So if we solve equation 1 as written here for delta H, we will have the same problem of accuracy identified before, because we take the green slope here calculated with the water depth at the starting point. So we should use equation 2 instead of equation 1, as done before. However, as now the unknown is precisely delta H, the procedure becomes implicit, because delta H appears on both sides of the equation. So to apply this procedure, iterations will be required. Let us consider the same example as before. So we have the discharge, friction coefficient, slope, and the values of HU and HC that we had found before. We would like to calculate the water depth at a distance of 500 meters, so at the abscissa S equal 500 meters away from the gate. We could simply use the previous results and interpolate to find the water depth. As we have said, this is correct if the water profile is sufficiently smooth around the point we are looking for. But if it's not the case, like for example the end of the M3 profile, we need to use the procedure described here. So we will use the integration by increments of delta S. With 10 steps, we have a delta S of 50 meters. And we now have to fill the table using iterations at each delta S step. To find the water depth at the first point of abscissa 50 meters, we calculate N and D and then delta H using the equation here, taking the initial depth H in a fully explicit way, because we have no other estimates of delta H. With this first approximation of delta H, so delta H1 here, we will start the second iteration using the equation here, in which we can now calculate N and D with the interpolated depth as indicated here, H plus delta H1 divided by 2, where delta H1 was the result of the first iteration. We obtain a new value for delta H, that is delta H2 here, and we see that in the present case, delta H2 is slightly different from delta H1. We finally perform a third iteration in the same way, and we see that now delta H doesn't change anymore. So it's not necessary to add a fourth iteration for the computation of this delta S increment from the abscissa S equal to 0 to the abscissa S equal to 50 meters. Doing this for all abscissa in the first column, We can fill the table and find a water depth 500 meters downstream from the gate. That is this depth here. We also check, of course, that for each abscissa, 3 iterations are sufficient, as the final delta H is equal to delta H2 here. However, in some cases, the convergence might not be so good. For example, as we have said already, close to the critical depth, where the slope of the water profile becomes very steep. So finally, how to select the appropriate procedure? The integration by delta H increments in equation 1 is always stable and will often be the preferred choice. The only inaccuracy that could occur is at the last step when approaching the normal depth, where the computation yields a finite value that does not exactly correspond to the expected asymptotic behavior close to the normal depth. But when we need to know the water depth at an exact location, to avoid interpolations between 2 points of the water profile obtained by this first procedure here, it could be more convenient to use the second procedure with delta S increments. This procedure might, however, not converge in some cases close to the critical depth. The denominator becomes very small in that case, or even equal to 0, and the procedure does not converge because the local slope of the water surface becomes too steep. Now, another question is, how can we adapt the procedure to calculate water profiles in non-prismatic channels or even in natural rivers? As we can see from this Haitian example, a natural river is far from being prismatic. So this means that if we want to adopt an approach similar to the one presented before, we should take into account all the terms of the differential equation, including the term with dA ds. This can be done for gently varying cross-sections, like a progressive widening of a rectangular channel, for example, as dA ds in this case could be easily calculated. But it is more difficult for irregular cross-sections as those illustrated here. So in practice, for cross-sections of irregular shape, a better adapted procedure is to use directly the Bernoulli equation, written here between two cross-sections of different shapes. In this equation, J1, 2 represents the head losses between sections 1 and 2. These head losses can be of two different types: general losses due to friction and local losses due to local singularities. The friction losses are calculated as the average value of SF, the friction slope, at each cross-section, and SF can be calculated using Manning's formula, for example. The local losses are generally determined from the difference in kinetic energy between the two cross-sections, with a head loss coefficient zeta. So, if we develop the water level as the sum of the bed elevation ZB, that is the elevation of the talweg in the cross-section, and the water depth H, we finally obtain equation 3. In this equation, we see that all variables depend on the water depth, either H1 or H2. So, we will need to determine the geometrical characteristics, wetted area, wetted perimeter, hydraulic radius of an irregular cross-section as this one for any possible depth. As the cross-sections are usually represented by polygonal lines, as here, this can be done by dividing the cross-section into trapezoidal subsections, from which the total area and the total perimeter can be calculated. So, if, for example, the water profile is calculated from upstream to downstream, as in a supercritical flow, we know the conditions at cross-section 1 here, so we know H1 and we look for H2. In the same way, for a subcritical flow calculated from downstream to upstream, if we know H2, we can calculate H1 with this equation. But in any case, we see that this will lead to an iterative procedure. That is finally the basis of most of the available softwares designed for open channel flow calculations. Let us apply this type of calculation to the Agbado River in Benin. The portion of the river that we analyzed is represented here, and we see that the cross-sections are quite irregular. So the question here was to determine the water level immediately downstream from the dam. There is a dam somewhere here, without knowing exactly the downstream conditions. For the flow conditions indicated here, so a discharge of 50 cubic meter per second and this Manning coefficient, we can calculate the critical depth in each cross-section. This is this red line here, the red dashed line. There is no normal depth in the cross-sections because therefore we should have a prismatic channel in order to be able to determine the bed slope as 0, which is of course not possible here. Now if we consider, for example, a downstream water level of 116 meter, that is above the critical depth, as we see here, we can calculate the subcritical flow from downstream to upstream until the upstream end of this river ridge. A first observation is that the water profile is much smoother than the bed profile. If we increase the downstream water level to 117 meter, we obtain this new water profile, and we see that it progressively converges to the first one in the upstream direction. If we now decrease the downstream level to 115 meter, we obtain this third profile that also converges to the same depth at the upstream end of the river ridge. If we compare these three water profiles to the M1, MU and M2 profiles, we can see that we have overall a similar tendency, and we can consider that the upstream water depth represents a kind of equivalent uniform flow in this natural river. It is also interesting to notice that the upstream level is independent of the downstream conditions, at least for a certain range of downstream conditions. So, perturbation to the equilibrium flow induced by changes of the downstream boundary conditions can only affect the flow over a limited distance. In this case, far away from any downstream perturbation, the flow converges towards an equilibrium situation that is equivalent to a uniform flow. So, we are now able to calculate water profiles in different types of channels. But we have also seen that some profiles, like the M3 profile, have a limited length. And we now will have to see how such a profile can continue beyond the point where it reaches the critical depth. This will be for the next lesson. Goodbye!